Good morning, Ben Cohn, dot products and cross products. So the reason I want to talk about these is before you get to calculus, it's always kind of assumed that you'll talk about dot products and cross products sometime later. And then after you've gone through calculus, everyone kind of assumes that, well, you probably already learned cross products and dot products sometime prior. And so the result is some people just never learn it because it kind of gets lost in the shuffle. And then the people that do learn it, they tend to learn it kind of poorly. So I'm going to cover it now just because, and I'm not going to cover it in very much detail, but kind of give you the general idea of what you need to know for it. So the idea with dot products and cross products is they're two separate things, but because they both deal with vectors and they're both kind of learned at the same time, they're assumed to be similar. And they're not even really that similar. They're just a tool. So all of math is just tools. You have, if you think of like back to addition, you have one apple plus one apple, and you have two apples. Well, if you think about it in reality, that's not really true at all, because no two apples are alike. Even if you have two of the old same type of apple, like Macintosh or Golden Delicious, Red Delicious. Either way, you have two apples. They're not going to be exactly the same. So you can't be like, okay, I have two apples put together, or have one apple, the other apple put together, and you have two apples. Really, one apple will be better than the other, so it won't be equal. But addition is a good tool. That way you can kind of estimate, all right, I have all these apples, I have 300 apples. And it's a good estimate of like, okay, they're all kind of similar. And so when you look at addition, it's just a tool. Same thing with multiplication, exponents are just tools that you can use to make your life easier. And that's the same thing with dot products and cross products. So there's nothing magical about dot products. There's nothing, deep and philosophical per se. It's just a tool for you to represent physical phenomena. If there weren't physical phenomena in the world that you could represent using dot products, then the whole concept wouldn't exist. It'd be pointless. It'd be like, well, why would I bother caring about this abstract idea when this abstract idea isn't going to be able to make more food or energy or machine tools or whatnot in life? So start off by saying we have a dot product. We'll represent it as A. Move this over, move that over, slide. A dot B. I'll make little arrows to show that they are vectors, and this will equal something. And the way I'm going to represent what a dot product is, I'll just draw a triangle. The way I'm going to draw this is how this dot here, you initially think, oh, multiplication. No, that's a dot product. There's only supposed to be one T and no L. Okay. So you have, let's say, vector B, vector A. Then what this represents is the amount of A in the direction of B multiplied by the length of B. So if we say start at the same place, so that would be similar to, I'm going to write A vector B, and this is just going to show the amount of A in the B direction, and then multiplied by the length of B. So if B was like a length of 3, then this would be 3 times AB, the length of A in the direction of B. Another way of saying this is this will be the length of A times cosine of theta, where theta is the angle between the two, times the length of B. So this A dot B, or A times cosine theta, this gives you the amount of A in the direction of B, and then times B, which is the length of B. So this is useful because there's a lot of phenomena where this kind of applies. Another way of looking at this would be called this kind of comes down to the idea of projection. So you could say the projection of A onto B. So if you look at, let's say, A dot B hat, where by hat I mean it's a unit vector. It means there's a length of 1. So redrawing this, we could have something like b hat, unit vector, and a, where this would be the length of a in the same direction of b, so a projected onto b, and then we multiply it by the length of b, which is 1 since it's a unit vector. And so this would just be, as I labeled before, a, b. And even though I draw the little vector sign up there, the dot product always gives you a scalar. When you do a dot product, you start with 2 vectors, and it gives you a number. A number is just a scalar, 0, 1, 2, 3 halves, etc., etc. And so the big goal of dot product is to show you how much things are in line. It projects one vector onto another. So to throw out an example here, so let's say you have an expensive painting, both emotionally and culturally, and you have some sort of wind going this direction. I'll say a wind vector. And you have your painting, the way you're carrying it, one of those standard rectangle paintings, as a vector which is perpendicular to the side. So the idea is you're walking across the street with this painting, and then you could use the dot product, some sort of force thing, not technical, vector, would equal, kind of sort of equivalent to your wind vector dot your area vector. And so the idea here is the dot product. And that's going to be magnitude of wind times, this is just a multiplication, times area times cosine of theta, where theta is the angle between your wind vector and your area vector. So if you're carrying this painting across the street like this, the wind's coming this way, then the area vector, which is perpendicular to the painting, will be in line with your area vector. So cosine of theta would be 0. And cosine of 0 would be 1. And so you'd have maximum force from the wind on your painting, which would kind of make sense. If you're carrying your painting like this, wind is coming this way, it's going to do a lot of blowing of your painting. And so the idea then is you want to turn your painting sideways so that the vector that's perpendicular to the area of the painting, your area vector, would be pointing, instead of this way, go to blue, be pointing up. That way the theta between the two would equal 90 degrees. Cosine of 90 degrees is 0. It'd be much easier to carry your painting through the wind when the plane of your painting is parallel with the wind. And so that is one of the ideas of where this dot product would be useful. The physical phenomena behind this is more along the lines of work equals F dot dr. You'll see this in physics, if you haven't seen it already, where work is defined as force times a direction vector. So the amount of work that's done on an object, it's how in line the force is with the direction of motion. The other thing that the dot product is useful for, and you've probably seen the calculation already for how to do the dot product. So let's say, for example, that our A vector, zoom in a bit, go to pen, go to blue, our A vector equals, let's say, A1, A2. And our B vector equals B1, B2. And the idea here then is we have a coordinate plane. We have a vector like this, vector like that. This is our A, and this is our B. B1, B2, and then similar for A. And it would be, just looking at it, things are kind of difficult to see what the theta is between them, but we might want to project A onto B. And so the way we can do this is A dot B equals, and this is kind of sort of mostly true, you do A1 times B1 plus A2 plus B2. And this will be equal to the magnitude of A times the magnitude of B times cosine theta. This is also a really interesting way of finding what the theta is between two vectors by doing this equation right here. So the value of A dot B is, you have this formula for finding how in line one vector is with another. And then you can also use that formula to find the cosine, or the angle between these two vectors. So you could kind of think of the dot product as giving you how in line they are, or how parallel two vectors are to each other. So one of the other useful tricks for dot product is you can use it to find the length of a vector. So for example, if you have your vector A and you do A dot A, what that's really saying is how in line is this vector with itself. And that will give you the length of a vector. So if we do this in math terms, to say we're going to stick with our A1, A2 here, we do A1, A2 dot A1, comma, A2. Have the little brackets to show that they're vectors. And this is A dot A equals, yeah, my A's kind of look like 2's, sorry about that, equals A1 times A1, that's just a, they're not vectors, so it's just multiplication, plus A2 dot, or times A2, which gives us A1 squared plus A2 squared, and that equals the magnitude of A squared. And if you think back, that's basically the Pythagorean theorem, because our A1 vector is giving us our x, our A2 is giving us our y, and then we square them both, and that gives us our length squared of the whole vector. Now, to go off, not too far off the deep end, but a little bit, one thing to be not worried about, but another way to look at this is, if we have A1, so I'm going to clean up the board just a little bit. I'll leave the formula up here. And I'll rewrite it. We can do a better job rewriting that. So we have, our idea is A dot B, two vectors, equals absolute value, or magnitude, of A times magnitude of B times cosine of theta, where theta is the angle between the two. So we're going to say we have A1, or A, equals A1, A2, where this is coordinate system, and we have A1, A2. Well, another way of looking at this is the x value here is A1, this is A2, and so we can say that A equals A1, I'm going to say times x hat, which is the unit vector for x. Hat is not an actual technical term. Plus A2 y hat. And the idea here is we can break this up into a whole bunch of small unit vectors. And then just add them all together. And the unit vectors will be length 1, so there'll be a number of unit vectors in proportion to A1 and A2. So now let's look at this again. So if we do A dot A like this, then what we get is something along the lines of A1 x hat plus A2 y hat dot. This is multiplication. No, that's the dot product. Sorry. This is dot product. A1 x plus A2 y. We FOIL this, and we're left with A1 squared x hat dot x hat plus 2 A1 A2 x hat dot y hat plus A2 squared y hat dot y hat. That's dot products. And so what's important about this is we know that the dot product is the magnitude of each times the cosine of theta. So the magnitude of each of the unit vectors is 1. That's why they're unit vectors. And then the angle between them is either 0 or 90 degrees. Or pi over 2 if you prefer. And so the cosine of 0 degrees, so the cosine of 0, would just equal 1. This is cosine of pi over 2 since the x and y unit vectors are perpendicular. So then this would make this 0, and then this would be 1. And the reason I point this out is, and then this would then give you the Pythagorean theorem which we had before, which gives you, so the magnitude of a squared is a1 squared plus a2 squared. But the reason I point this out is at some point in life you might come across different basis vectors. When you create your coordinate system, you can create a coordinate system using any two vectors that are linearly independent. And the idea with linearly independent is basically that they're not pointing in the same direction or the opposite direction. And so if you have two vectors, just anything like this, you can then get to any point you want just with a linear combination, a combination of many of each. And so the idea that not all basis vectors, not all coordinate planes will have basis vectors, x hat, y hat, which are perpendicular. But they are chosen to be perpendicular so that when you do the dot product, use the Pythagorean theorem, you get this x squared plus y squared equals c squared, or z squared, type relationship. And so if you ever see planes, coordinate systems that aren't, one of the first things you need to realize is, okay, this Pythagorean theorem isn't going to work anymore. I'm going to have to go back to the basic idea, and the basic idea here is dot product. So the dot product, so the two useful things about the dot product is it tells you have two vectors, take a dot product of each vector, it tells you how in line these two are. And the way you do the dot product is this. I should probably write up the other part. Let's do some more blue. We'll do blue. So this would be A1 times B1 plus A2 times B2. And if you have more than two components of the vectors, it's 3 dimensions, 4 dimensions, then you can continue on as well. So this is when people memorize something for dot product, this is usually what's memorized. And pretty useful. So that's the first thing that dot product is useful for. The second thing that dot product is useful for is finding the length of a vector. So when you can use the dot product to find how much in line one vector is with the other, i.e. the projection. And when you project a vector onto itself, then they'll tell you how long it is. This is A in the B direction. And so dot product dot itself gives you the length. Okay, so that's the idea behind a dot product. The cross product is written as A cross B. There we go. So the dot product, it gives you a scalar, but the cross product, the idea behind a cross product is it will take two vectors and it will give you a third vector that is parallel to each. So one of the ideas is if you have your coordinate system, your x, y, and z, the coordinate system is defined as x cross y equals z. And the way you do, there's lots of different right-hand rules to find the direction because there's two parts to a cross product. There's direction and magnitude. So the magnitude is going to be given, do this real quick, equals magnitude of A times magnitude of B times sine of theta. The way I remember this is it would be awfully darn convenient if the cross product used cosine because they both start with C and they sound kind of similar. Not true, not convenient, it's just a trap. And so the cross product actually uses a sine. So magnitude of A times magnitude of B times sine of theta will give you the magnitude. The other part is the direction. So the way the direction works is you already know that it's going to be parallel to both. So if you looked at x and y here and kind of imagined it as a plane, then you could say that, all right, this is going to be perpendicular to that. But then you're given two directions. So the definition of the coordinate system is x cross y equals z. And the way I do it, there's lots of different ways to do it, is you point your hand in the direction of the first vector, in this case it would be x, and you cross it with y. So it's a motion action. By doing an action, it kind of helps me keep it in my head. Mnemonics are good, but the more senses you can get into your mnemonic, I think the better. And that's why I try and do an action. Some people are just like, pow, right hand rule. And it's like they remember the fingers go this. I like to do it in order with motion. So I do point in the x direction and then bend my fingers in the direction of the second vector. So it'd be x cross y equals z, pointing up. And so if you look at this coordinate system right here, where x is going to the right, and we'll say y is going into the board, so it'd be x cross y, and z is pointing up. And this is the definition of the coordinate system. And that's why, so if you had something like this, it would actually be backwards. You need to have the y going down for it to be this coordinate system that we use. Right-handed coordinate system, if you will. Okay, so now that you know, it's going to give you a direction and a magnitude. And the direction is point your hand in the direction of the first vector, turn your fingers to point towards the second vector they're crossing, and then your thumb will point towards the resultant vector. This is really useful for a handful of things. The big one to come across is, I think it's called the Lorentz Force. Basically I say force electric equals QE, which I think is Coulomb's law, plus QV cross B. And this is, I think, called the Lorentz Force. And it's basically the idea if you have a charged particle moving with some sort of speed in a magnetic field, then it's going to feel a force that's perpendicular to both the velocity of the charged particle and the magnetic field. This is why in physics you'll see a lot of questions where a particle enters a uniform magnetic field and then the particle basically starts moving in a circle. The other instance, one that would be a little bit more intuitive, is if you're working like on a wrench, on a nut. And so basically, top view here, you have some sort of nut, probably hexagonal. And you want to tighten or loosen it. You get your wrench, also semi-hexagonal in nature. And there's probably a little hole up there. And the idea when you want to tighten it, the formula for torque equals R cross F. So the magnitude of torque without the vector, would be magnitude R times magnitude F times sine of theta. So what the sine of theta means is this is your radius, and this would be then your force. And the idea is, if you've noticed when you're pulling on a nut with a wrench, bigger wrenches are better. And bigger wrenches are better because it gives you more moment arm. Moment arm? Is that the right name? I don't know. More radius to pull with. But then when you pull, you also want to pull perpendicular to the wrench. And by pulling perpendicular to the wrench, you're going to get the most effective torque. So, and intuitively, you think that you'd want to pull that direction as opposed to this direction or that direction. And you want to make your force that you pull as close to 90 degrees as possible. And by doing 90 degrees, you're going to get the best torque out of it. And the way you find the amount of torque is R cross F. You usually learn that in first semester physics. And that's one of the times that a cross product will pop up. Now your thought process might be, okay, so do we have a formula kind of like the dot product before the cross product? We do. I'm not going to talk about it. It's the determinant. So you can look it up on the interwebs if you'd like. When you need to actually know it, you'll be taught it. Probably. The big thing to know about the cross product is just the idea that you have two vectors that when you do one vector across the other, so it's one vector across two vectors gives you a resultant vector. It gives you the direction and then the magnitude of each multiplied by each other. So a cross product sort of measures how perpendicular two vectors are, where the dot product measures how parallel two vectors are. And this is all the introduction you really need for this calculus. At some point in life, if you continue on, you'll do more with them. But this is kind of really just the foundation you need. So next time, I'll go over some more integral examples, kind of do a little bit of review problems. And after that, that's going to wrap up what's done for the course. I appreciate you guys watching. Hope this helps a little bit. And I will see you guys next time. Thanks.